Lincoln Parish Park is a 15-minute drive from the heart of Ruston, Louisiana and Louisiana Tech University. Centered around Hoogland Lake, this park features a 1.25-mile walking path around the lake and a 10-mile mountain bike trail. Adding to the existing amenities in the park, such as pavilions, campgrounds, and fishing piers, is a planned disc golf course which will cross a new man-made river. To facilitate the crossing of park visitors, employees, and park maintenance vehicles, the University of Waterloo Steel Bridge design team has been tasked to build a steel bridge.
Established in 2014 with 4 awards and 7 competitions under its belt, the University of Waterloo Steel Bridge design team is at the forefront of innovation in this field. Together, the design, construction, fabrication, and PR and finance sub-teams collaborated throughout the year to submit the design proposal for the Canadian Student Steel Bridge competition.
The first step in our design process was to look at the site constraints. We then looked at bridge designs from previous years that might work well with those constraints and modeled them in SAP 2000, our structural analysis software, to understand why these bridges worked well and what their shortcomings were. We adapted elements from different bridges to create a design that had the lowest deflection and was simplest to construct. We then iterated on those designs based on our SAP 2000 analysis. We then used Excel to optimize the section design and sizes of steel pieces and check for failure. Once the final design was decided on, we completed our detailed design modeling using SolidWorks. Our bridge design is a response to the constraints that were inherent to our site conditions, such as a wide river, an asymmetric site, and a limited envelope. The bridge envelope limited us from including a large arch, and the site obstacles required us to design a bridge, especially the connections, around ease of constructability.
The most prominent features of this bridge lies in the design aspect. The bridge uses sturdy truss members capable of supporting themselves as a top chord for ease of constructability. A second under truss maximizes use of the available depth in the bridge envelope. The design of the top chord in terms of increasing moment of inertia is, first of all, identifying what we want to improve under the envelope restriction that doesn't allow an arc. We decided to rotate the stringer, resulting in a wider horizontal section, which increases the moment of inertia during the lateral loading. Moreover, the combination of knee braces and outrigger truss legs shorten the effective span of the bridge, which reduces deflection for the entire structure. The highlight with this year's bridge design is a main connection for the stringer. It features a tongue and groove connection for ease of constructability and a double shear connection for extra strength. The double shear connection has 2 shear planes running through the bolt, resulting in a double load capacity of the bolt. This design also resists bending due to the angle that acts similarly to a moment connection.
The connection of our bridge is also very important in guaranteeing ease of constructability. Our wedge connection design is optimized for strength while also being very simple to slot in from a distance, while our improved triangle connection from last year is easier to align in areas with tight fits. Lateral and under truss connections were designed with crush tubes to prevent damage during assembly. Our bridge also uses wide leg plates, allowing builders to leave them freestanding during the initial periods of construction. Our construction process takes place with 2 builders on one side of the river, 1 on the other side, and 1 in the middle, which helps make connections over the river easier. The builder in the river assists the solo builder. Some pieces needed for the main truss are passed over from the other side of the river to the solo builder via the river builder to prevent them from having to let go of the structure. Once the first side of the bridge is installed and is standing freely, builders on both sides are able to assemble the under truss in a similar process and then finally add the lateral members.
After completing and testing our design, we then moved to fabricate the components of our bridge through the university's very own engineering machine shop. All detailed designs were drafted in-house, and the materials were ordered from local businesses to maximize efficiency. To fabricate our bridge, a water jet was used to create crevices and connections. This involved taking a 1-inch thick plate and using a water jet cutting machine to precisely cut out the shape. With this water jet technology, less material was wasted compared to typical subtractive manufacturing, as the cutting process can be optimized to closely fit the clevis shapes on the plate. It also allowed for precise cutting and enabled us to meet proposed designs with high accuracy.
The University of Waterloo Steel Bridge team extends its heartfelt gratitude to our esteemed team members, generous sponsors, and dedicated faculty members for their invaluable contributions throughout the year. Thank you for your unwavering dedication and belief in our collective vision.